Good afternoon, everyone, and welcome to AEESP Converging COVID-19, Environment, Health, and Equity. This is session 4, and today we're actually going to be speaking on COVID-19 and sustainably supplying food, water, and energy. Before we go any further, I want to show a video welcoming you to this conference series.
The Association of Environmental Engineering and Science Professors, AEESP, is made up of professors in academic programs throughout the world who provide education in the sciences and technologies of environmental protection.
As hard as we work in our domain expertise, we need to work equally as hard to build positive human relationships with our colleagues, our students, and the communities that we serve.
We will continue to work towards a more just, equitable, and healthy society.
The goal of the virtual conference, Converging COVID-19, Environment, Health, and Equity, is to bring together different disciplines of environmental engineering and science to discuss actions to form a more healthy, just, and equitable society.
The conference themes align with the National Academy of Science, Engineering, and Medicine's grand challenges for environmental engineering in the 21st century. And they are
COVID-19, systemic biases, and environmental engineering in education.
COVID-19, fostering informed decisions and actions.
COVID-19 and the creation of efficient, healthy, and resilient cities.
COVID-19 and sustainably supplying food, water, and energy.
COVID-19 and designing a future without pollution and waste.
COVID-19 and climate change mitigation and adaptation.
Each session, as much as possible, will look at the convergence of air,
water,
wastewater,
food,
people, the built environment,
waste, fostered by the COVID-19 pandemic, and the unfolding realities of the need to address inequities in our communities.
Faculty from the University of South Florida and the University of California, Merced, are pleased to hold this virtual conference with support from AESP and the National Science Foundation's CBET program.
Gives me great pleasure right now to introduce Dr. Pablo Cornejo, who is an assistant professor at the California State University, Chico, in the Department of Civil Engineering. Dr. Cornejo is going to be the moderator for today's session. His research focuses on the life cycle environmental impacts of centralized and decentralized wastewater and resource recovery management strategies and sustainability frameworks for water treatment systems. Dr. Cornejo is passionate about teaching and interested in increasing the participation of underrepresented students in science, technology, engineering, and mathematics fields through interactive, project-based sustainability education. He's also a great musician. And Dr. Cornejo received a BS in Civil Engineering with an emphasis on water resources and environment from the University of Colorado Boulder. He obtained his MS and PhD degrees in environmental engineering from the University of South Florida and conducted postdoctoral research at the University of Colorado at Boulder. Welcome, Dr. Cornejo.
Thank you, Maya. I'm tuning in here from Northern California, and just briefly, before I get started, I'd like to acknowledge and be mindful that Chico State stands on the lands that were originally occupied by the first people of this area. We recognize the Mechoopda and their distinctive spiritual relationship with the land and the waters that run through our campus, and are also humbled that our campus resides on sacred lands that were once sustained by the Mechoopda people for centuries, and acknowledge that the Mechoopda are still here doing their work. Today, we are going to be talking about Grand Challenge 1 from the National Academies of Science, Engineering, and Medicine. And that challenge is to sustainably supply food, water, and energy for the 21st century. This challenge comes from their recent consensus study report and discusses the fact that providing life's essential food, water, and energy for the world's growing population is a major challenge. Doing so in a manner that does not threaten the environment and the health or productivity of future generations is an even bigger challenge. To contextualize this challenge, the world's population is growing and urbanizing, in which we have a larger population of people living in urban areas than rural areas. According to the United Nations, there's an estimated 60% increase in food production that will be needed to feed 9.3 billion people by the year 2050. And population growth is related to increases in water demand. All the while, climate change exacerbates problems associated with water quality and water scarcity, especially in drought-prone areas. Additionally, globally, energy demand will increase as 1 in 7 people in the world currently live without electricity. There are equity implications associated with this grand challenge. Communities worldwide face challenges related to their sustainable supply of food, water, and energy. And COVID-19 has exacerbated these challenges. For example, disruptions in food supply chain call for a need for innovative, resilient, and localized food production through innovations in farming techniques. This is especially true in Black, Brown, and Indigenous communities that face challenges in both urban and rural settings. Equity issues are also relevant in places such as the Navajo Nation, in which the provision of clean water, renewable energy, and sustainable food supplies are crucial. COVID-19 has disproportionately impacted many Indigenous communities. So a lot of the talks in this session will focus on opportunities to build resilience through innovative techniques and address these challenges. We also have speakers that will discuss the importance of wastewater treatment and resource recovery during the global pandemic. The Global Pathogen Project, for example, focuses on the importance of access to scientific data to address water and sanitation issues. And another speaker will be discussing the importance of researching antibiotic resistance and the formation of superbugs in wastewater streams. In summary, the environmental engineering grand challenge, number one, highlights that advancing sustainable agriculture to feed our growing population is going to be necessary. Increasing agricultural yields and reduce life cycle environmental impacts is important. Also, addressing food waste challenges is important, in addition to environmental injustices and challenges of hunger. Overcoming water scarcity in terms of improvements to our supply, distribution, and efficiency are crucial, and clean water and clean energy are crucial for this challenge to meet increases in global demand. We can approach this through systems thinking, life cycle thinking, resource recovery-based research, and research on resilient systems to improve global outcomes. With that, I'd like to introduce Dr. Weslyn Ashton. Dr. Weslyn Ashton is an associate professor of environmental management and sustainability at the Illinois Institute of Technology, Stewart School of Business. Dr. Ashton's research focuses on industrial ecology, optimizing water, energy, and material resource flows in socio-ecological systems, and developing entrepreneurial solutions to social and environmental challenges, particularly in low-income and developing regions. So, Dr. Ashton, welcome.
Thank you, Pablo. Today, I'm going to be talking about how local supply chains can support innovations in food production and delivery. Next slide. As borders closed and states implemented stay-at-home restrictions, COVID-19 caused severe disruptions in our food supply chains, which was notably seen in things like empty grocery shelves and shuttered restaurants. Behind the scenes on farms, there were mixed effects. My research group pivoted from our activities to participate in an outreach program with Illinois farmers to understand COVID impacts on their operations. Some reported being severely handicapped due to not having enough laborers to work on their farm to safely tend and harvest crops, not being able to access processing facilities or distribution centers to get their products to customers, or meet new safety requirements in those distribution centers or farmers markets. But we also heard from some that business had never been better, that demand for local produce skyrocketed. And if they had the infrastructure and resources to get products to urban consumers, they were almost guaranteed high sales. Next slide. Even before COVID, we had begun exploring ways to increase sustainability and equity in local food supply chains through institutional purchasing and business models for the aggregation of produce from small farmers. This included a statistical analysis of food hubs across the US to understand their organizational structures, services offered, and profitability. Since COVID, we have been inspired by the dozens of innovations that have emerged in the local food supply chain, where alliances of small farmers and operators have been collaborating to share resources, procure and deliver nutritious food to households across the income spectrum. I'd just like to highlight two examples from Chicago. So on the left is Close Loop Farm, which is a medium tech vertical farm that gets its name from recycling 99.5% of its waste. It primarily served restaurants and pivoted to selling via an online platform, and they brought their friends along, so neighboring farms and other food production businesses offering pickup and delivery across the city, and new innovations such as this salad club that's shown here in this photo. On the right is Chai Fresh Kitchen, which is a worker-owned cooperative whose workers are formerly incarcerated individuals who specialize in meal preparation for Black and Brown communities. They partnered with local farms, other food service co-ops, and community organizations like churches to provide culturally appropriate meals to food insecure communities. Next slide. My group studies material energy and waste flows and network dynamics in industrial ecosystems, which embody the concept of a circular economy, effectively utilizing resources and recirculating them as much as possible. We're seeing a number of initiatives like the plant pictured here emerging across the city, combining business incubation for sustainable urban agriculture, including vertical farming and food businesses, with material synergies across firms to reuse byproducts, shared management of water resources, and digestion of food waste to recover energy and use the digestate as soil amendments. These new models are also proposing health centers to be located inside their facilities to provide education and health services related to food for the communities in which they're located, such as a Veggie RX program where doctors prescribe vegetables instead of medicines. Next slide. As we develop new innovations to produce food in cities, such as through controlled environment agriculture, we need to balance the emphasis on technological advancement with cultural needs and equity concerns in the places where these enterprises are developing. Pictured here on the left is AeroFarms in Newark, New Jersey, which uses aeroponic technology to mist precise amounts of water and nutrients to leafy greens grown in vertical stacks. Vertical farming has many environmental benefits, such as low water use, no pesticide use, but it does have significant energy consumption concerns. It requires high technology, software, and robotics, but few employees. It's receiving significant private equity funding, which stands in stark contrast to the underinvested urban communities in which many are located, and the sparse financial capital flowing to Black and Brown entrepreneurs who are interested in starting such businesses. So equity in financing urban agriculture at various technology levels needs to be addressed, as does cultural appropriateness of offerings grown in such enterprises. The photo on the right is taken at a nearby school where AeroFarms has installed a growing stack to educate kids at the school about growing their own food which is served in the cafeteria. So COVID has exposed the many problems in our highly industrialized food supply chain, but it has also shown the power of local food production and collaboration for the delivery of nutritious food to diverse communities. What lies ahead is forging to create equitable circular economies in food production, consumption, and waste management to ensure that Black, Indigenous, and other people of color have access not only to healthy food, but also being able to prosper from the economic opportunities to produce it. Thank you. Back over to you, Pablo.
All right, thank you so much, Wesleyan, Dr. Ashton. Our next speaker is Carletta Chief. Dr. Carletta Chief is an associate professor and associate specialist in the Department of Soil, Water, and Environmental Sciences at the University of Arizona in Tucson. She's the director of a National Science Foundation National Research Traineeship, Indigenous Food, Energy, and Water Security and Sovereignty. Her research goals to improve our understanding, tools, predictions of water shed hydrology, unsaturated flow in arid environments, and how natural and human disturbances affect soil hydrology through the use of physically based methods. Dr. Chief is Dene, originally from Black Mesa, Arizona, and received a BS and MS in civil engineering from Stanford University. And as a National Science Foundation doctoral fellow, Dr. Chief received her PhD in hydrology and water resources in the School of Engineering at the University of Arizona. So welcome, Dr. Carletta Chief.
Thank you to AEESP Converging COVID-19 hosts for inviting me to this panel. I am Bitterwater, born for near the water people. My maternal grandfather is mini goats and my paternal grandfather is red running into the water. That's how I identify myself as a Dene Navajo woman. I'm speaking from the University of Arizona, which is located on the traditional homelands of the Tohono O'odham and Pasco Yaqui people. Next. COVID-19 has amplified food, energy, and water, or FEW, insecurities across the world, and disproportionately impacted Indigenous communities. Next, in the United States, COVID-19 is rampant on the Navajo Nation, the largest tribe in the United States, where poverty rates are more than twice the state of Arizona. Navajo tribal officials cite lack of healthy foods and running water as reasons for the prolific transmission, which in May 2020 resulted in one of the highest COVID-19 infection rates in the United States, third only to New York and New Jersey. Next. In the United States, Native Americans have the highest rate of diabetes. Comorbidities such as diabetes and cancers are also prevalent on the Navajo Nation. With over 500 abandoned uranium mines, Navajos are at risk to environmental exposure from abandoned mines. On the Navajo Nation, arsenic is prevalent in unregulated water sources, often used for drinking water. Research has linked arsenic-laden waters to diabetes. Next. Few insecurities have been amplified on the Navajo Nation during the COVID-19 pandemic. The Navajo Nation is a rural food desert with only 13 grocery stores across the 25,000 square miles of remote terrain for a population of nearly 200,000 tribal citizens. This is approximately 8 people per square mile. Furthermore, 30% of remote Dene homes lack running water and 40% lack electricity. The Dene people haul water 5 to 50 miles away, incurring an enormous expense of $13.30 per 100 gallons, in comparison to a nearby city of 40 cents per 100 gallons. Community resilience is critical for Dene communities to respond to and recover from perturbations such as pandemics and disasters. Next. Developing technical solutions to these challenges requires an understanding of Indigenous societies, governance, and culture, and the ability to work effectively in these contexts. Thus, the INDIGEFUSE program's vision is to develop a diverse workforce with intercultural awareness and expertise in sustainable food, energy, and water systems, specifically through the design of a fit-for-purpose water and control environmental agriculture technologies to address the lack of safe water, energy, and food security in Indigenous communities. To develop this workforce, in partnership with Diné College, our project, Indigenous Food, Energy, and Water Security and Sovereignty, or INDIGEFUSE, is educating and engaging graduate students and tribal college students with an emphasis on recruitment of first-generation and minority students seeking opportunities to make a difference in developing communities. Next. The overall research theme is the development of a novel and sustainable solutions for off-grid production of safe drinking water, brine management operations, and control environmental agricultural systems. This includes research in innovative photovoltaics, holographics, sensors and controls, unit operations technologies, and material device and system resiliency. Next. Community resilience is critical for Diné communities to respond and recover from pandemics such as COVID-19. Resilience is the ability to maintain desired structure and function of a few socio-ecological system under perturbation, such as COVID-19. Yet, outside of health metrics, few resilience frameworks often fail to consider Indigenous perspectives. Existing resilience frameworks aim to co-manage resources and empower Indigenous people still remain part of an unjust and colonial system and fail to consider political, social, and cultural perspectives. Engaging Indigenous communities is important to increasing the Indigenous resilience, which may improve, for example, sustainable water resources research and management, and facilitating addressing fused insecurities among Native American communities. Few technologies can augment adaptive capacity to transform system state to desired structure and function, thus increasing resilience at multiple scales, such as household, community, and tribal nation. Next, thank you very much.
Thank you so much, Dr. Carletta Chief. Up next, our next speaker is Dr. Matt Verbila. Matt Verbila is an assistant professor of environmental engineering and director of the Safe Water Research Lab at San Diego State University, SDSU. His research, teaching, and service activities are related to water and wastewater treatment and the study of microbiology of engineered and natural water systems. Dr. Verbila has a BS in civil engineering from Lafayette College and a master's and PhD in environmental engineering from the University of South Florida. Welcome, Dr. Verbila.
Thank you. Thank you. So my talk today is on pathogens and partitioning in resource recovery systems. Next. So wastewater treatment systems, we know, take sewage and produce a treated liquid effluent. However, they also produce a solid residual called sludge. And when we talk about the flow of pathogens through a treatment system, oftentimes the focus is just on what the removal is between sewage and treated water, the liquid effluent. However, some pathogens have a greater affinity and attraction to the sludge. And if we were to consider the removal just from the liquid part, as in the difference between the sewage and the liquid effluent, compare that to the overall reduction, which is the difference between the sewage coming in and what's leaving in the liquids and the solids, the two calculations would produce different results. Next. So what causes pathogens to be more in the sludge versus more in the liquid? So some pathogens have a greater attraction to solids. They end up more in the sludge than they do in the liquid. And certain technologies have the need to remove sludge more frequently. And certain wastewater treatment technologies also produce different types of sludge with different characteristics. And all of these factors affect whether or not pathogens end up in the liquid effluent or in the sludge. Next. So this is results from a study that our students did in collaboration with colleagues at University of Minas Gerais in Brazil at a research and training center in Belo Horizonte. This is a pilot scale sewage treatment system that uses anaerobic technologies combined with algae-based technologies for treating wastewater. Next. We measured the concentration of virus indicator, coliphage, in different points throughout this treatment system and found that the viruses had a low affinity to the solids and they were mostly found in the liquid effluent. Now, in contrast to that, other groups have reported that SARS-CoV-2, the virus that causes COVID-19, has a potentially higher affinity to solids and is regularly detected at higher concentrations in the sludge. So depending on which pathogen is of interest, they might be more prevalent in the liquid effluent or they might be more prevalent in the sludge. Next slide. So why is this important? It's because in some places, the sludge is actually more valuable to farmers than the liquid effluent in terms of resource recovery and using the resources in wastewater for food production. So here's an example of a project that we have in collaboration with the National Water and Sewerage Corporation in Uganda for a treatment system serving the city of Kampala, where the liquid effluent is discharged to a river and not reused, but the sludge is picked up by farmers and used for soil amendment to grow food crops in the region. Next slide. So our objective here to try to promote greater equity in terms of managing the safety of food, energy, and water systems is to open up access to scientific data. So the results presented previously from our study would normally be published in a journal article, which may only be accessible to other scientists and may be not open access and may require a payment or a library subscription to obtain the data. So what we're doing through this project is producing a database that has all information about water pathogens that's open and accessible for anyone to use. And along with that database, we're producing a tool that practitioners can use to create meaningful outputs that can help them make decisions about resource recovery and safe reuse of water and biosolids from sludge. Next slide. So this is an example of that output for the system in Kampala, Uganda, where this system treats both sewage and fecal sludge from on-site sanitation technologies. And this is a chart that shows the prediction of how viruses flow through the system. So the viruses tend to end up more in the liquid effluent rather than the sludge and the biosolids. Next slide. Whereas other types of pathogens like helminthids, which cause diseases like intestinal parasites, will tend to end up more in the sludge and biosolids. And even within those pathogen groups, there may be differences from one to another, like the example of viruses. Some viruses may tend to end up more in the sludge than others, while other viruses may end up more in the liquid. So if we compare the removal to the overall reduction, there's actually a big difference if we look at just the liquid effluent or if we look at the system in terms of the sludge and the biosolids as well. Next slide. So why do we care about this, and how does this relate to global pandemics and COVID-19? So some pathogens, like I mentioned, are larger or they have other properties which make them more likely to stick or to have an affinity to the solids. So some pathogens may end up more in the solids than they do in the liquids. And some treatment technologies produce more sludge than others. Combined with that, sludge is more valuable than treated wastewater in some places, and the opposite is true in other places. The treated wastewater may be more valuable than the sludge for resource recovery. In terms of COVID-19 and the use of wastewater surveillance, SARS-CoV-2 concentrations in primary sludge have been used in several research studies throughout the world as the basis for wastewater-based epidemiology or wastewater-based surveillance. So understanding how pathogens partition between liquid and solids is important for using these types of methods to manage global pandemics. Next slide. That's all. So I want to appreciate the contributions from our students and from our colleagues for this work.
Okay, thank you so much, Dr. Verbila. Our next speaker is Dr. Anjali Muchandani. Dr. Anjali Muchandani is a postdoctoral fellow in the water and energy efficiency for the Environment Lab, at Stanford University. Anjali will be joining University of New Mexico as an assistant professor in 2021. Her research involves global water, waste, and energy challenges by developing novel materials and physical chemical processes to improve resource sustainability. Two unique resource reservoirs she studies are the atmosphere, capturing drinking water from the atmosphere, and sewage sludge, recovering metals, nutrients, and energy. She received her PhD and MS in environmental engineering from Arizona State University and BS in civil engineering from University of California, Los Angeles. Welcome, Dr. Mulchandani.
Thank you so much. My name is Anjali Mulchandani, and today I'm going to be talking about atmospheric water capture, a decentralized off-grid emergency water supply. Next slide. As Carletta mentioned, COVID-19 highlighted water challenges in rural and remote areas, in particular the Navajo Nation. Prior to the start of COVID, the EPA estimated that 40% of the Navajo Nation did not have access to running water, and instead had to travel to wells. However, these wells can be contaminated by uranium or fecal matter. And COVID exacerbated this water crisis. And as now we need water for more than just drinking, we need it for sanitation and we need it to wash our hands. In times of emergency, one of the immediate solutions is to transport water by tanker trailer or cases of bottles. But this can be even more difficult and expensive during a pandemic. Therefore, there's a need to provide safe, clean water off the municipal water grid with the flexibility and safety of bottled water, but without the associated cost and waste. Next slide. So how do we get water during a pandemic? Typically, we think about our liquid water supplies like rivers, lakes, groundwater. But these sources can be inaccessible or contaminated. But there's another reservoir that we haven't talked about yet, and that's the atmosphere. And the atmosphere actually has 6 times more water than rivers. It's just stored as water vapor. And the great thing about the atmosphere is it's universally present. We can access it anywhere and at any time. And atmospheric water capture was inspired by the Namib desert beetle, which actually captures fog on its back to serve as its drinking water supply. Next slide. So how do we as humans and engineers capture water from the air if we're not the desert beetle? Well, we can use a technology called a desiccant. And you may be familiar with desiccants as the little white packet that you'll find in a shoebox or in your leather goods or even powdered food. Or if you work in a lab, you may use desiccants in a desiccator to keep your samples dry. And desiccants work by adsorbing water vapor on the air onto its surface. And once a desiccant is saturated, it's exposed to heat, such as sunshine, to desorb that water vapor so it's close to saturation. Then we can cool, condense, and collect that water as a liquid. And desiccants are typically housed in a box as shown on the right. It's about a cubic meter in size, so the size of a U-Haul moving box. You can collect water by adsorbing, desorbing, and condensing. Next slide. So how do we as environmental engineers take our scientific understanding of desiccants and apply it to provide water to those in need? Well, we can apply tools in our arsenal, like geospatial informatic tools, atmospheric climatic tools, and even material science and engineering tools. In the upper left, I show relative humidity across the United States in the summertime. And the purple box shows that the Southwest is relatively arid, with humidities between 10 and 50%. But this region has abundant sunshine, which can provide sufficient energy for water vapor desorption. We've been able to tailor-make photothermal nano-enabled desiccants specifically for use in regions at 40% humidity with abundant sunshine. These desiccants are superheaters, so similar to how you would park a black car outside in the sunshine, it'll superheat. So we can see in the graph at the bottom right that these desiccants will uptake water at 40% humidity and then quickly release that water when they're exposed to sunshine. And we can cycle these materials back and forth to produce up to 2.5 liters of water per meter squared. So this is enough for 1 or maybe even 2 people's drinking or sanitation supply. Imagine now if we can scale up and modularize these units to provide water at a household or even at a community scale. Next slide. So as environmental engineers, we're also curious about the quality of the water that's produced. Is it safe for use? Is it safe for us to drink? So here we show an example water quality profile for dissolved organic carbon. And you can see that the concentrations vary temporally throughout the year, depending on your local air quality. Therefore, the type and the level of treatment that's going to be required, such as filtration or disinfection, is going to vary based on the location and the time of year that these systems are going to be operated. Next slide. So to conclude and talk about the convergence of atmospheric water capture and COVID-19, my take-home message to you is that while we face challenges in the water sector during pandemics, droughts, or other disasters, there are opportunities to leverage environmental engineering, atmospheric science, and material science and engineering for developing creative solutions to sustainably supply water to all in need. Next slide. And with that, I want to say thank you for listening to my talk. If you are a student interested in working on these topics or a faculty or industry member interested in collaborating, please reach out to me at anjaliem@unm.edu. Thank you.
Hey, thank you, Anjali. Up next, we have Dr. Tala Navab Daneshmand. Dr. Navab Daneshmand is an assistant professor of chemical, biological, and environmental engineering at Oregon State University. Dr. Navab Daneshmand researches the fate and transmission pathways for pathogenic and antibiotic-resistant bacteria from wastewater systems to environmental reservoirs, as well as the design of engineered systems to reduce and combat contaminants of emerging concern. Dr. Navab Daneshmand was a postdoctoral researcher in Switzerland and a postdoctoral fellow in Montreal, Canada, and received her PhD in environmental engineering from McGill University in Montreal, MS in environmental engineering from Tehran University, and degree in civil engineering, bachelor's in civil engineering from Amir Kabir University of Technology in Tehran. Welcome.
Thank you for the introduction. I'm going to talk about antibiotic resistance crisis and its relation to the agricultural reuse of wastewater and biosolids. Next, please. With the increase of population worldwide predicted to reach 10 billion by the year 2050, there will be agricultural demand increase. And therefore, as discussed in this panel, there will be need for alternative resources in agriculture in terms of irrigation or soil amendment. Wastewater and biosolids being rich in nutrients and can be used as alternative resources. There are regulations in effect by different regulations agencies for microbiological quality, for reuse of wastewater biosolids in agriculture. In the US, these regulations are set by the Food and Drug Administration and Environmental Protection Agency in terms of enteric bacteria such as E. coli, which is a fecal indicator bacteria. What these regulations do not include are the human health crisis of antimicrobial resistance. Next, please. What is antimicrobial resistance? When bacteria become resistant to antibiotic treatments, that's referred to as antibiotic resistance or antimicrobial resistance. Another term I'll use is multi-drug resistance, and that is when bacteria become resistant to not just one or two, but 3 or more classes of antibiotics. This is referred to in media as superbugs. Just to put it in context, in the US alone, according to the most recent CDC report, there are annually 2 million infections due to antibiotic resistance, causing 35,000 deaths. The widespread use of antimicrobial therapies during the COVID-19 pandemic is reported to have increased in some countries. And these increase in antibiotic treatments during the COVID-19 pandemics are generally due to co-infections and secondary infections. Therefore, the pandemic has potentially increased the burden of antimicrobial resistance. The burden of antimicrobial resistance is also disproportionately affecting low and middle income countries and communities. This is mainly due to the insufficient supply of clean water and sanitation infrastructure, but also due to high potential for transmission of pathogens in these communities. Wastewater and biosolids being the treated sludge, as discussed by Dr. Verbila, my colleague earlier, are one of the main reservoirs, recipients, and resources of antibiotic-resistant bacteria and their determinant genes. So therefore, next please. Therefore, one of the gaps in the knowledge that in my research group we are trying to address are the time variance of antibiotic resistance in wastewater. So how does it change with time? The prevalence and abundance of antibiotic-resistant bacteria and genes, and their fate in soil after wastewater irrigation and biosolids amendment. Next, please. To address these gaps, we performed a study in a greenhouse setting at Oregon State University, where we had these 2-gallon pots and we planted carrots from seeds. We watered some groups with water and some groups with wastewater effluent. We added soil amendments in terms of biosolids to some groups. And we continued the study for 11 weeks until we harvested carrots. During this time, we collected weekly samples of soil and we collected samples from the wastewater effluent. And at the end, at the harvest, we also collected carrot samples. And we tested all these samples for prevalence and abundance of antibiotic-resistant bacteria and genes. Next, please. So here, I just want to talk about the time variance of antibiotic-resistant genes in wastewater effluent. On the left-hand side, you see a figure where on the x-axis, there are the target antibiotic-resistant genes that we looked at. And on the y-axis, there is the normalized concentration of these target genes, normalized to 16S rRNA. We measured the concentration of these genes, and then we did statistical analysis to see whether there was significant time variances for these genes during these 10 weeks of the study. We didn't see a significant time variance between these genes, meaning the concentrations remain relatively constant throughout the 10 weeks. And these 10 weeks were between winter, late winter and early spring in Oregon, where there was a significant temperature change and a significant change in precipitation. However, those did not impact these concentrations. On the right-hand side, you see correlation matrix between the correlation between these target genes that we looked at. The red boxes are showing significant correlations that are highlighted by some stars. There are many correlations and many conclusions from this figure. However, what I want to point out to is the column on the right, INT-I1 gene, is an indicator of multi-drug resistance. So this gene was strongly correlated with 3 of the genes we looked at. And these 3 genes, SOL1, SOL2, and BLAST-CDXM, could, because of their correlation with this multi-drug resistant genes, could also suggest being indicators of multi-drug resistance. This can potentially be used in forming policies and regulations for antimicrobial resistance being an indicator for in policies. Next, please. In this figure, you can see the concentrations of total and antibiotic-resistant E. coli and enterococci, total on the top, and the bottom ones are antibiotic-resistant targets for E. coli and enterococci. It's a crowded figure, but what I want you to take from this figure is that if you can see, they're so overlapping that you can't see, but we have water irrigation and wastewater irrigation in solid and in dashed lines. And there's no significant difference. There was no significant difference observed between the concentrations of either total or antibiotic-resistant target bacteria when we use wastewater irrigation compared to water. However, when we applied biosolids to soil, those are the red lines with circle symbols, the concentrations of total and antibiotic-resistant E. coli and enterococci increased in soil, but it increased significantly. But what was interesting was that the antibiotic-resistant bacteria declined at a significantly faster rate than the total counterparts. And that's good news. So they're not persisting as far as the total counterparts. However, we did see majority of multi-drug resistant enterococci in these soil samples. At the end of the harvest, we saw that carrots harbored E. coli, majority of which were resistant to ampicillin. Next, please. So at the end, I would just like to emphasize that antimicrobial resistance is an emerging human health concern that can potentially be exacerbated by the COVID-19 pandemic, disproportionately affecting low and middle income communities. With the need to reuse wastewater and biosolids in agriculture, we need to pay specific focus on this crisis and understand how it affects different practices and different policies. Next, please. And at the end, I would like to acknowledge Catherine Mays, who was a graduate student in my research group and led the studies we just discussed, my colleagues, and the U.S. Department of Agriculture for funding this study. Thank you.
Okay, thank you so much to all of our panelists. I would like to invite the panelists to turn on their cameras for a Q&A. And I would like to also invite any people in the audience to submit questions in the Q&A as they come up. To start things off, I'd like to just ask a question to all of the panelists to see if you can speak to the following. What role does equity play in your research and teaching? And how do you incorporate equity in your research and teaching? And so we can start with perhaps Dr. Chief to speak on this topic.
Thank you, Dr. Cornejo. Equity is central and driving the work that we do. Much of the work that we have done has been built with the community in listening to their concerns, developing partnerships over many years. So the research that we do doesn't happen on our end alone. We really work with the Navajo Nation to direct us as to what are the needs and concerns that they have. In addition, we work with the oldest tribal college in the United States, Diné College. And so what we're doing is we're building pathways to support the tribal college students to pursue education and careers in food, energy, water systems. Because these students, these tribal college students, are students that want to work in their communities. They want to return to their communities. And many of them don't want to leave their communities. So we want to work with the tribal college to provide the tools that they need so the students can stay within their communities, solve the food, energy, water challenges within their communities, and co-design with the communities. So the communities is really driving everything that we do. And we work with the grassroots and nonprofit organizations as well.
Thank you so much. I'd like to direct this next question to Dr. Weslyn Ashton. I'd like you to touch on this issue of how you integrate equity into your research, as well as speak on, related to this theme of convergence, and given what the other panelists have talked about after hearing the presentations, in which ways can we make our research more equitable, and in which ways can we make our research more convergent?
Thanks, Dr. Cornejo. So in my work, I always try to approach from a position of humility. So I work primarily with Black and Brown communities in Chicago, and echoing Professor Chief's comments, it takes a long time to build relationships with organizations, with communities, to get them to trust us, that we're not just using them to collect data, but instead are able to really listen to what their needs are and to direct our research in a way that supports the things that they need, and that we're able to work collaboratively to identify what are their priorities and structure our research to serve those priorities. I think that it was very interesting listening to all of the presentations, right? And so food, energy, water are so interconnected. And there's a theme of health, I think, that also threads through this seminar series. And so it's, how do we utilize our resources more effectively? And so how, as engineers, and I'm trained as an engineer, but currently work in business and design. And so it's converging that technical expertise and understanding that as we develop new technologies, we also have to be open to working with others on the behavioral side and understanding the economics of technical solutions, and how we often think of technology as neutral, right? Technology is not neutral. And so equity concerns do come into how technology is being developed, who's developing that technology. And so I feel that, in thinking about convergence, we need engineers, we need economists, we need sociologists, right? And we need a close collaboration with communities to understand how the work that we're doing serves those needs, and can prioritize different aspects of research, technical, economic, what have you, as is needed.
All right, thank you so much. And I'd love to just open up the floor to any of the other panelists that would like to address the two opening questions related to what role does equity play in your research and teaching, and how can we make our research more convergent after hearing the other presentations and panelists.
Sure. I could talk a little bit about one thing we're doing on the teaching side here at San Diego State related to equity. So I'm working with a group of 2 other faculty in our department of Civil, Environmental, and Construction Engineering to bring some research into the classroom in sort of a self-study. So what we're doing is we're working with a social scientist, graduate assistant, and another professor who's developed this tool to code the way that we interact with students in the classroom. So we have our classrooms recorded with the consent of the students, and we focus on which students participate in the classroom and what types of participation they, how they communicate with us and how we respond to their communication. So it's a way for us to see that data, and for me personally to understand, maybe how I can better understand implicit biases I may have with the way that I respond to students, and structure my teaching to kind of engineer a situation that elicits more equitable participation from students. So that's something we're doing at SDSU related to equity in the classroom.
Great, thank you so much. Perhaps we can go to another question. Feel free to answer the question related to equitable outcomes and achieving those equitable outcomes, in addition to how we can make our research more convergent. But we have a question from Fernando Roman, who asked this question from Twitter. What are some recent advancements in sustainable technology that you are proud of? And this seems like it may be a good question for Anjali, but whoever would like to take it is free to.
Yeah, I'm really excited about technologies that are truly, truly decentralized, that are able to give communities the capability to serve their own water, energy, food, sanitation needs on their own. And I think this is where atmospheric water capture comes in, not having to rely upon liquid water supplies, understanding that those can be contaminated. It's really exciting for us to see that. And speaking to the idea of equity and convergence, I'm really excited to hear from people like Carletta and Wes, who talk about working directly in the communities. And I would love to see the convergence of having people who've done work in communities and surveyed communities to understand their needs and figure out how we can then tie that to technological solutions to provide independence and water capability to all.
Great, thank you so much. Perhaps Dr. Navab Daneshman can speak to this question of both equity and convergent research before we move on to another one.
Yeah, sure. So, as discussed, for example, when we talk about the problem of antimicrobial resistance or other problems, it's very important to consider the communities, not only the communities we live in, and not only the communities around us, but the communities that are disproportionately affected by the problems that we study. And if we only find solutions and we find the whatever gaps in the knowledge that we're trying to understand in one community, that might not work for all communities. And if we have a holistic approach, meaning considering all communities, but also a holistic approach of, for example, in this panel, we're talking about food, water, and energy. If we consider everything together, human health, and bring engineering to this whole holistic approach to find a solution, then that would give us a much better solution that would serve all and would consider all parameters.
I'd like to chime in, Dr. Cornejo. I think that it's one of the things that we're really proud in DigiFuse is that we've developed these off-grid systems with the community. So it's a co-design approach, which requires a lot of iteration. And then at the same time, training our science and engineering students to have intercultural awareness, to be immersed in the community, to understand what the perspectives and the worldviews of the community are, so that they're not just coming in doing helicopter research, designing something that would not work with the community. And so part of the success of the technology has to be adopted by the community, which means that the community has to have the skills to operate and maintain the system. So with our team, we're working with social scientists to look at what are the perceptions of the Navajo people to these off-grid systems. Is it something that they want to adopt and to maintain into the future? So I think that's really critical in this technology innovations, is that we're not just designing the best and the greatest, but really, is that design going to be adopted by the community? And will they be able to operate and maintain it into the future? So it's really also working with the community's workforce and developing their workforce to also adopt this, and also stimulating their economy as well. So we're trying to identify community partners who would be able to take on these technologies, help it to create more jobs, and make that technology more available to the greater Navajo Nation. Thank you.
Absolutely, yes. And I one thing that I would add to that is that this long-term commitment to sustainability, long-term commitment to communities is very important in conducting research here with disenfranchised communities in the United States, as well as communities abroad, and some of the international research, to not just swoop in and think we fix something and leave, right? But have a true long-term commitment. I have a question here related to COVID. This is a question that came in from Munim Mur from Gmail before. And the question is, and I'll open it up to whoever wants to answer it, how can we use the current changes to our lifestyle and energy demand from the COVID era as an opportunity to reimagine our shift in energy system and cleaner energy, more resilient energy systems when we go back to life under a life without COVID? And I'm open to any insights from any of the panelists on that feel inspired.
I think that for the communities that I work with on the Navajo Nation, it's really revitalized the traditional livelihoods that the people have had for centuries, such as ranching, farming. And so those communities that have really held on to that are now the role models for other communities, and they've had good produce and good harvest as a result of this revitalization. And I hope that it'll continue on into the future. And I think for the indigenous communities that I work with, their conservation practices have been an example for us to reduce our energy use, our consumption. And so I hope that that has been a wake-up call for us to be more sustainable locally and to support those local communities in their sustainable practices. Without the pandemic, they didn't have as much support, but now people are looking to them, wanting to learn how to do sustainable farming and be more self-sufficient. Thank you.
I can add something as well as just, I think the idea of doing a conference like this, we've definitely realized that through our work and through our interactions with others, we don't always have to get on a plane and go somewhere. We can have, an effective communication with people from all over the country or all over the world, even with these digital tools. So, to reduce the energy and carbon footprint of our own activities, I think is an important lesson learned from this pandemic.
I'd love to just add on to both of these comments. And I think that we need to look at the institutions and policies that create the demand. So thinking about off-grid energy. So in the city, we have City of Chicago. We have a number of initiatives that are thinking about having these self-sufficient industrial ecosystems, taking food waste, doing anaerobic digestion, converting that into energy, but they're not able to sell back to the grid, or the cost of integrating that technology back into the grid is so high that it's a real barrier. And so I think that there needs to be a recognition from the established institutions, so whether that is the electricity supply companies. If we're talking about food, it's the food supply chain and the institutions that do large purchasing, recognizing the importance of local generation and diversifying the system to provide some of that resilience. But I think we are seeing openings and innovations happening across food, across energy, across water. But we need to change the structure to enable those innovations to take hold and proceed after the pandemic.
Thank you so much. If anybody else wants to speak to this COVID-19 issue, great. I have a question specifically for Tala, and I'm wondering, are greater use of disinfectants during COVID-19 also causing more antibiotic resistance?
Thanks for the question. The use of disinfectants certainly affects the microbial communities in the wastewater treatment systems. I am not sure about the specific impact of the current pandemic on the use of disinfectants in relation to antimicrobial resistance, but it does change the microbial communities in treatment reactors. Therefore, it is a good question to look at. However, I don't think that would be a significant contributor to the emergence of antibiotic resistance.
Great, and so we have a great discussion going on here. We have about 15 more minutes, and we still have some questions coming in. I have a question here specifically for Dr. Ashton and the group in general, whoever wants to address this. Do you think announcements of investment into Black and Brown communities for home ownership, such as Bank of America and Chase, have a chance to translate into more intentional academic collaborations with economists and engineers? So I think this speaks to interdisciplinary research and convergent research. This is a question from Joe Bozeman. So thank you, Joe.
Thank you, Dr. Bozeman. I think that we as academics have to be really intentional about the work that we do and how our research, whether by not paying attention to it, we contribute to the infrastructures that perpetuate systemic racism. And so if we're talking about, the siting of power plants or wastewater treatment facilities that are primarily in communities of color and low-income communities here in the U.S. and across the world, we need to, to challenge the assumptions that the technologies we're designing are neutral and have neutral impacts on different communities. And so I think there's a real need to be more intentional and recognize how our work contributes to racism, or can intentionally work to dismantle that systemic racism. And so I think it's an intentionality that we don't always confront in our research, whether it's single disciplinary or multidisciplinary. I think having collaboration across disciplines, especially bringing in anthropologists, helps to bring those insights, recognizing, when are the impacts of the designs that we're developing going to affect different communities, create more harm in particular regions. And so I think, the call is really for, being more aware and intentional about how our works can contribute to racism.
Wanted to just allow for a little bit of Zoom awkward silence to see if anybody else wanted to chime in there. We're all getting accustomed to that. But I did want to address a question for Anjali. So this is a question that was in the chat, but for the people on YouTube and the people that are watching outside of Zoom, I'd love for you to address this question on, so the comment was fascinating material development and idea for using atmospheric water. At what scale would this have an impact on precipitation in nearby areas? And this is a question from Shannon Capps.
Yeah, thank you so much for that question. It is a very relevant question. I mean, it really comes down to what is the scale of atmospheric water capture that you're going to perform relative to the scale or the volume of water in the atmosphere. And based on some of our analyses, we found that if we're doing this at a small household or local community scale, you're going to be collecting less than 1% of the total volume of water in the air. So overall, there should not be a large climactic influence. However, if we decided to scale these systems up to be larger and provide water for everybody, then there definitely would need to be an additional study of how it's going to change our local climate. I do want to add on to some of what Wesleyan was saying about creating equity in our research. So some of the things that we're working on at Stanford are making sure that we work on inviting scholars of different backgrounds to our research groups. So how can we create equity in the pipeline of students who are applying? So one of the things that we are working on are open collaborative lab resources that we'll be able to place online, working with students of different backgrounds to include them in our research, to include different perspectives, and making sure that we're providing opportunities to everybody to interdisciplinarily collaborate on these topics.
Great. Thank you so much for that answer. I have a question here related to COVID-19 and the connection between outbreaks and meat processing plants that we've seen. So what have we learned from COVID-19 outbreaks in meat processing plants specifically that can be prevented, changed in future pandemics? I think perhaps this is related to antibiotic resistance, related to wastewater in animal feed operations. And this is a question from Hope Hauptmann. Thank you, Hope.
So the question was about Sorry, I missed the beginning of the question.
The question is related to what have we learned about COVID-19 outbreaks in meat processing plants? You know, that have been certain centers that have had high COVID-19 outbreaks, and how might we prevent or change this in future pandemics?
Thank you. That's a very good question, and that's one of the meat processing plants could be one of the sources that we need to look at for antibiotic resistance. And if in fact we could have what we don't want to happen is to have an outbreak of the so-called superbugs, and one of the places for these to happen could be meat plants and animal farms. So there are many things you can think about, and we need to focus on the use of antibiotics for treatment for example for animals in their feed being one of them. So we need to really focus on regulating the prescription and the use of antibiotics and antimicrobials, whether it's in for animal feed and for humans as well. We need to really focus what we're doing and what we're consuming to avoid the further emerging this concern.
Yeah, I could add to that too. I think just another thing in general that the public has learned from this pandemic is that pathogens don't necessarily only originate from other humans. So like the knowledge that this was a virus that started in infecting bats and transitioned to another animal before it evolved into mutated into something that can infect humans. The idea of zoonotic, what we call zoonotic pathogens, that's something that is now public knowledge. And so it's important that we manage food, energy, and water systems using kind of a One Health perspective, where we're not just thinking about human waste as a potential hazard, but also animal waste.
Absolutely, yeah. And I think that's important for many different concentrated animal feed operations, for example, in the US, as well as smaller scale systems. This is a question for Dr. Ashton. I also think that Dr. Chief might be able to address this issue. Some areas have begun to shift to more localized food supply chains because of vulnerabilities exposed by the pandemic. The question is, do you believe this will last through and beyond the end of the pandemic? And I like this because I think it addresses the importance of localized food supplies to address the provision of healthy foods for communities. So any comments on that would be fantastic.
Yeah, I was also thinking about addressing the meat processing question, but from the economic side, because what we see here, and it relates to this question, is that we've had a highly efficient industrialized food supply chain, but what that includes are choke points along this supply chain. So the meat processing plants were a key part of that. And so we had farmers who had to kill the pigs, kill animals on their farms because the backlog to get into the meat processing plants because of COVID was running into months, right? So there was a bottleneck and high demand at the meat processing plants to process animals into meat. And I think, so there are similarities in other parts of the food supply chain. There is a significant push amongst local suppliers, so that includes farmers, it includes policy advocates, to build upon the relationships and the innovations that have emerged in response to COVID. And I think that there is a real fear that because we have such high efficiency and low cost in the conventional supply chain, that it's going to be very easy to switch back into that mode, right? And so right now we see customers demanding more local food because it's available, and in a way that, during the height of the pandemic, the supply chains were disrupted. And so I think we need to, one, sort of work with consumers, try to build and encourage consumers to consuming and demanding food that is produced locally. There's also a need to institutionalize contracts. And so whether that is with organizations like public schools or, government agencies who have a large demand, universities, right, that can provide the demand for local food producers to continue that relationship, right? So it's not just a one-time thing. And finally, I think there are policy shifts, right? So I think to my earlier point, there's a need for institutional change, structural change, policy change that can keep the demand for that more local, more diversified food production and supply to help continue these positive trends that we've seen.
I think it would be easy for us to forget once, if the pandemic ever ends, if it were to be in that new normal. I think it'd be easy for us to revert back. And I agree with Dr. Ashton that there needs to be the structural change and the policy change. But I also would agree with Dr. Verbla that in this virtual world, there has been connections made with industry to connect with NAVAJO chapter governments to be innovative and think about contributing to the economy of the local chapter community, to look into vertical farms and ways that can not only stimulate the local economy, but also supply food to the local food chains in these various grocery markets. We have individual farmers, nonprofits that have been doing local traditional farming for many years, and it's hard work. It's especially with dry land farming, where you're not connected to irrigation system. So in order for those traditional farmers to continue, I think they need that type of support from the policies, grants, other ways to allow them to continue doing that type of traditional farming, and then passing it on to their children, because I think that's where there's a disconnect at times with our community, is that many of the young people are out, in urban settings, being modern, and they're not at home engaging in that traditional type of farming. So there's a lot of different levels that need to come together to really make that significant change. And I hope that we can do that now, work on that now while we're in this phase, and hope that will be part of the memory, a permanent change, and that we won't forget once we go back to the new normal. And that's what I really hope for.
Thank you so much. And I think that, not only resilient food systems, in addition, a lot of small communities, decentralized communities face tremendous challenges on the wastewater front, aging infrastructure challenges, and a need to innovate and make sustainable decisions from a social, environmental, and economic perspective in wastewater management, resource recovery, and drinking water provision, as well as sustainable energy sources. I think we have time for one more quick question, and then we'll wrap things up, I believe. This question is for Anjali. It's a question on Twitter from Colleen Naughton. Besides dissolved organic carbon in the atmosphere, in atmospheric water capture, are there issues with mercury or other chemical compounds? Similar issues as, things that you would face with acid rain, for example?
That's a really good question. So we've tested various types of atmospheric water capture devices, those that are desiccant-based and those that are simply condensation-based using refrigerants and compressors. And we find that the type of technology that you use impacts the quality of the water that's produced. So when you use a desiccant-based system, we've measured 27 different environmentally relevant metals, particularly those that are regulated by the EPA primary and secondary drinking water limits. And we find that they're well below the maximum contaminant levels for desiccant-based systems. However, when you use a simple condenser-based system where you're just collecting that water vapor and condensing it to a liquid, you do see various metals in the water that are being collected from that atmospheric air. So my answer to that would be the type of technology that you use and the location that you implement it in is going to then impact the level of treatment that will be required for a specific use case scenario. There's no one-size-fits-all solution. Thank you.
Absolutely. So how do we move towards more fit-for-purpose systems? How do we move towards appropriate technologies for our food, water, and energy systems in rural communities, in urban communities, globally, locally? How do we move towards more equitable solutions? I'd like to thank everybody for coming to this session. We do have some brief announcements about upcoming sessions right after this, but in summary, this was a session about the sustainable supply of food, water, and energy. We had a great list of speakers from around the country that joined in and panelists to talk about their respective researchers. So I'd like to thank Dr. Wesley Ashton, Dr. Carletta Chief, Dr. Matt Verbila, Dr. Anjali Muchandari, and Dr. Talat Nawab Daneshmand for their participation as panelists. And I'd like to thank everybody that came on YouTube, on Zoom, for joining in. And I'll hand the mic over to Maya for some final announcements on future sessions.
Thank you, Pablo, and everyone. That was an excellent session. I think we got through quite a bit of the Q&A. So thanks for folks who have sent in questions. We will be posting the Q&A on the AESP Converging COVID-19 site. This is the first session that actually got through most of the questions and answered online also. We do have a quiz that goes with this session. You could click on the QR, take a picture of the QR code there, or find it also on our AESP Converging COVID-19 website. You do get Envision credits for attending these sessions. And just like to say that coming up next week, we have COVID-19 and designing a future without pollution and waste. I know there were some questions on energy that I think some are going to be answered next week. And just to wrap up and say really thank you to the sponsors, the organizations involved here. A big shout out to the Strong Coast program. I see some of our advisory board members are participating, including some of our partners from the Barbados Water Authority, the National Science Foundation, AESP, of course, USF, and the University of California at Merced, and the cohort of staff and students from both institutions who have made this a success. So thank you again to those logging on and to our amazing panelists. You guys are so efficient. And I really hope that we can carry on these conversations, especially since there's so much interest in working in the places and the communities with whom you work. Thank you so much.